Honey, don't walk out, I'm too drunk to follow. You know you won't feel this way tomorrow. Well, I'm paid all my tickets. Let me on the circle. Father will the soul rebels.
Hello, everybody. So after our usual musical introduction of us rebels, me and him, so we will pass on to more serious stuff. But first, let me tell you something. This is a guitar, right? And a guitar plays because it's strings. All the strings make different sounds, and they make different sounds from the thicker, which is a really big deep sound. And if I change guitar now, and I take a bass guitar, those of you who are not on a telephone, on a mobile phone, probably will hear the sound, but it's got even thicker strings. See? This one's got a sound thicker, thicker, thicker. So the thicker the string, the deeper the sound. Remember this because it become useful later when we're going to talk about strings. Just cutting off the guitar, and we move on to the subject. So yes, can you pass me on the presentation?
Yep.
Alex? Yes, okay, here we go. So today's subject is the theory of everything, right? Theory of everything. It sounds incredible to have a theory that encompasses everything. Well, it's not quite everything, it's everything about cosmology, particle physics. It certainly does not include things like medicine or dancing or theater. As usual, my disclaimer, I am called the man from CERN. This is what name you gave me, guys. But actually, I have worked at CERN for 35 years, and I am now retired. So this means that I am no longer affiliated with CERN. So what I'm saying is entirely my own responsibility and does not involve in any way the beliefs or the program of CERN. So said that, we can now start by looking at something that those of you who followed me in the previous episodes of this series and have heard about dark matter, about antimatter, about quantum mechanics, about relativity. And today we are going to tackle something that is a little bit more fundamental, such as the standard model of particle physics. This standard model is something, well, think of it a bit like the elements tables that you learn in school, where oxygen and hydrogen and everything, they are the names. But this is one step smaller. So we go inside the nucleus of the atoms of for instance, oxygen, helium, whatever element you want to take. They are all made of protons and neutrons, and inside protons and neutrons you find quarks. Right, now you're seeing this table is grouped according on the horizontal, if you look at it horizontally, you have quarks in blue, and I'll tell you in a minute what they are. Later, down there are leptons. So then if you look at it vertically, the first three lines are the three generations of fermions, which are matter, is stuff that you see, you can touch. These are all fermions. Me, I'm a fermions, as well as other things. But what makes me solid and not just a flash of light is actually the fact that, are the fermions in me. So on the other end, on the other side, here on the right side, you have the gauge bosons, which are those four, and they are, gluon, photon, Z boson, and W boson. And these are responsible, they're vector bosons, they're the force carriers. So they're the things that carry forces. So when the guy says, may the force be with you, actually he's talking to them, to these bosons, right? Or he's talking about them. That's the force that would be with you. So let's go back to the quarks for a second, and let's leave the Higgs aside for the time being, because it's the last arrived in this standard model, last discovered. So let's look at the quarks, right? As we said, quarks are what constitutes protons and neutrons, and any hadrons, that basically anything that has got mass. So, for instance, in the proton, you will find two up quark and one down quark. Think of up and down as two different quarks. They have different masses. One's much smaller than the other. And they are arranged in a certain way. So in the proton, you have up, and down. In a neutron, we'll have the opposite, down, up. And in fact, the mass of the proton or the neutron depends on the kind of quarks it contains. Then you have here on the second family, charm and strange, and then top and bottom. Now, these four actually do not exist in nature. They don't walk around our universe. We don't see them other than in transformation, in events of transformation of matter to energy and from energy back into matter. As I told you before, at CERN, we collide protons in order to completely disintegrate them into pure energy. This energy will then crystallize, or rather decay, I should say, into elementary particles that are only temporary for a very, very small fraction of a second. And we catch them for this fraction of a second in our detectors. And then they will eventually decay into something more stable, like, the particles that like protons and photons and electrons and etc. So these are temporary particles. And the top and bottom, in particular, the top quark is the most massive of the quarks. This is a guy that actually weights like, what, 8,000 times or something like that, 80,000 times. Well, it's a mass of 173 giga-electron volt, something, right? Say 173 something. It's not kilos, it's not grams, we measure their mass in electron volts, or rather in mega electron volt and giga electron volt, but just look at the number 173. Compare to, so this guy is 173 giga, giga like gigabytes, means billion of electron volts. And instead, the up quark, which is the one that composes protons, is like only 2.2 mega electron volts. So it's like, yeah, is it 80,000 times? Somebody with a machine? Right. Now, the guy on the right, the first guy has got gluon. Now, these guys, as I said, are the building blocks of the universe. And in order to build, you need building blocks, but you also need cement. You need a glue. And this glue is actually what is these gluons do. Their functions is to glue together the quarks inside a proton or a nucleus. Look at these little lines, wiggly lines in between the blue, red, and the two up quarks and the down quark in this proton. These are gluons. Now, gluons are the carriers of the strong nuclear force. This symbol up here, S, that appeared up there. That means that they are the guys that keep together the quarks to form a proton or a neutron. And the strong nuclear force is so strong that you can't push them, you can't pull them away from each other. They are so strong that you can't rip them apart, other than with a serious amount of energy. And this is, what happens when you're talking about nuclear fusion, when you're talking about even fission. What you're doing, actually, you're disintegrating the protons, etc., and transforming them into pure energy. This is what the LHC does as well. It puts proton-proton two protons in a head-on collision, and when they collide, both they transform into pure energy, because we go and break those gluons, and the whole thing disintegrates into pure, in a flash of pure energy, which lasts a fraction of a gazillions of a second before it becomes other particles, like I just said. So that's the gluon. Now, I've got too many mice here and keyboards, sorry. So I don't know what to type. Here it is. Below we have a photon. Okay, the photon we know is the carrier of, is the particle of light. We've seen photons, we discussed photons when we spoke about, Einstein's theory of relativity, of the special relativity, and we spoke about the photons, the speed of light. So, but the photon is also the carrier of the electromagnetic force. So we saw that all these particles can at the same time be particles or waves. We saw the double slit experiment, where very strangely in quantum mechanics, if you are not looking, then the particles behave like waves. And if you put detectors and you try to look at what they're doing to see them, then they behave like particles. So it's like they know that we're looking. Now, still down on the series of the orange balls down here, we have a Z and a W boson. The W boson actually is a double boson. It's negative or positive. It's got two different signs. These are the carriers of the nuclear force. We call the weak nuclear force, which is the one that's, for instance, in the sun, which for instance is in nuclear bombs. That's the weak nuclear force. And these are also particles that that are tracked by us at CERN. We study these particles to see how they behave. We also have on the this guy very well. Electron is the particle that is at the basis of everything: electricity, electronics, magnetism, chemistry. Anything you do these days is based on electrons in the modern world, right? There's all talk I'm giving and there's all interface computers and network is, of course, all based on electricity, electronics, and so electron is our guy. And below it, we have a very shy and elusive particle, which is the neutrino. Now, this one, the first generation of fermions, is actually exists in nature. And in fact, in this very second, I have about 10 billion of neutrinos that are passing through every centimeter of my body every second. We are under a constant rain of neutrino, and these neutrinos pass through us, through our body, not interacting. That means they don't even touch any of our atoms. They just pass through us like we were, I don't know, like a bullet in water, and even bullet in water will actually create a perturbation in the water. These things don't at all. They pass and they go through us without touching any of the electrons and the atoms, because their cross-section, a cross-section means basically imagine their size. They're so small that they don't interact with anything. They will, for them, an atom is like the whole universe, and they can pass through electrons. They can pass even through protons, etc., without even touching them. So neutrinos is, because it's so elusive, it's very difficult to detect. And we do have detectors, neutrino detectors, but we're trying to study them because he's a suspect culprit for a lot of phenomena. He could be involved somehow in dark matter, in antimatter. We believe, for instance, that it could be the reason why we exist, the reason why, antimatter has not prevailed with matter, and that we are made of matter today, and all the antimatter got disintegrated at the moment of the Big Bang. And this guy could play a role in that. We're not sure yet. We're still looking at the experiments. We have particularly one experiment at CERN, the LHCb, where B is for beauty. Now, beauty is a different name for the bottom quark. This guy here, the guy that's the blue guy up there on the third family. So top and bottom quarks are, part of these quarks that only materialize in our Large Hadron Collider, and we're studying. And we are hoping that this bottom quark, also called beauty, would be telling us something about the reason why matter prevailed towards antimatter at the moment of the Big Bang. Again, this is all things we've already covered. So for those who did not follow my talk on antimatter, please go back. You'll find it on the Facebook, on the Facebook site a few weeks ago. So let's let our London City girl tell us in an animated way about the standard model. Oh, she's gone away. She doesn't want to talk today. Come on, girl.
Standard model of particle physics. When we think of an atom, we generally think of a nucleus made up of protons and neutrons, surrounded by a cloud of electrons. If we look deeper into the heart of the nucleus, we realize that the protons and neutrons are made up of other particles called quarks. Quarks, like electrons, are thought to be elementary particles that make up our universe. The Standard Model categorizes all the elementary particles into either matter particles, otherwise known as fermions, or force carrier particles, otherwise known as gauge bosons. Fermions are divided into quarks and leptons. There are 6 quarks, up, down, chance range, top and bottom. There are 6 leptons, electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. The gauge bosons are gluons, photons, and the W and Z bosons. There are 4 forces that we know of: the strong force, the electromagnetic force, the weak force, and gravity. Gluons mediate the strong force between the quarks, holding them together within the protons and neutrons. Gluons also mediate the strong force between the protons and the neutrons, holding them together within the nucleus of the atom. Photons are particles of light which carry the electromagnetic force that holds the electrons in atoms. W and Z bosons carry the weak nuclear force, which is involved in some forms of radioactivity and plays a role in how the sun burns. The Standard Model also describes the Higgs field, which is a quantum field that permeates all of space. Particle interactions with the Higgs field imparts other particles with their mass. For example, the top quark is interacting with the Higgs field, and this is what is giving the top quark its mass. The Higgs boson is the local excitation of the Higgs field. And there's one final boson to talk about, the graviton. This is a hypothetical particle that mediates the gravitational force.
Right. So the point is, I did particularly not include the graviton in my model I gave you before because we have not found it yet. It's not yet, although it's a theoretically part of the Standard Model, we have no proof that it exists. Although we have measured gravitational waves, as we know that when there is a wave, there is a corresponding particle. However, we have never seen the particle. As for the Higgs, well, that's my favorite because the Higgs was the last thing I witnessed being at CERN, because the announcement of the Higgs happened on July 4 in 2012. And I basically left CERN I retired from CERN a month later. So mission accomplished, even though I didn't do much as for working on the research, but I helped with virtual reality modeling of the Large Hadron Collider. So it was a good achievement. Now, back to the Standard Model, that's your map to the universe. If you ever go to visit CERN, which I strongly advise you to do, you can walk out with a nice t-shirt or a cup that contains the formula of the Standard Model. And the Standard Model of particle physics is the base formula of the universe, of everything that composes the universe. But not quite everything, because the Standard Model is incomplete. It does not explain gravity. And like I said, the graviton has not been found as a particle. And it does not explain dark matter. We still don't know what dark matter is made of. Perhaps it's made of one of the particles that we have in the Standard Model, or perhaps it's something completely different. We don't know yet. And same goes for dark energy, which is responsible for ripping apart the universe now. I mean, it started the inflation of the universe, which had been kind of constant for all the 13.7 billion years, now suddenly is increasing. The universe is being split apart much faster than it used to be previously, in the previous billions of years. And black holes also are a problem because the mass fails when you go to the infinite gravitational pull of black holes, ripping space-time beyond, basically infinitely. So this model is incomplete. And we've seen as well, we've seen relativity, we've seen quantum mechanics, quantum theory of quantum mechanics, and today we've seen the Standard Model. But all three of these are sort of incompatible. Certainly relativity and quantum theory are not compatible, because whereas relativity talks in terms of space-time, which is a continuum pervasive, which is everywhere in the universe, quantum theory instead talks about quanta, which means quantized states. And for instance, we know that particles, like an electron, moves from a quantum to another quantum without passing from the space in between. It just dematerializes here and rematerializes there. So that goes against the formulas and the theory of relativity. And the standard model, like we said, also is incomplete because it doesn't contain graviton, which is gravity is the basics of general relativity. So we need something that can unify these three theories. And this something is what we call the theory of everything. The theory of everything means a theory that could reconciliate, we could harmonize these three theories and put them all under one simple set of formulas, one simple calculus. Now, this theory is believed today, or at least a lot of physicists today believe, I believe the majority of them, believe that this theory is the superstring theory. And we will talk about it in a minute. First of all, though, let's talk about string theory. String theory was the ancestor. We started by conceiving string theory back in the 60s. Former colleague of mine at CERN, Gabriele Veneziano, wrote a paper back then that was hypothesizing something like this, that basically the particles that we know, if you go and break them down, underneath you will find billions of times smaller things that are like vibrating strings. And this is why I was talking before about my strings on my guitar and on the bass guitar. These strings can vibrate at different frequencies, which must be unimaginably high because they're very, very small strings and very thin. They're like I think it's like, is it a billion times smaller than a proton, than a quark strings. So basically, by vibrating in different frequencies, they give birth to the different particles. So a string that vibrates in a certain way will be creating a quark, another one an electron, another one an electron, and so on. So again, let me quickly say that particles are expression of tiny strings that vibrate inside them. And this theory could unify general relativity and quantum mechanics, but it explains bosons, but it doesn't explain fermions. And fermions are what-given matter. And predicts the existence of tachyons, which are imaginary particles that travel faster than light. Somebody asked me before in one of the previous shows about tachyons. And well, these are, of course, imaginary because we know that nothing, if you want to accept, if you want to admit that the theory of general relativity is right, and we have no proof so far that it may not be right, there is nothing that can travel faster than light, faster than the speed of 300,000 kilometers per second. So there is a problem with this theory. And I'll let you, again, our friend,
what is string theory?
London City go.
String theory proposes that rather than the elementary particles, the fundamental building block of the universe are tiny vibrating strands of energy from which all the matter and all the forces in the universe emanate. Why string theory? The general theory of relativity and quantum mechanics are two of our most successful theories in physics. The general theory of relativity describes how the force of gravity works, and quantum mechanics describes how the other three forces work at the smallest of scales. But the two theories are incompatible. General relativity describes space and time as a smooth continuum, whereas quantum mechanics describes space and time as being quantized. String theory attempted to resolve the incompatibility and explain how all the four forces work, which made it popular, but it had a couple of issues. 1. The theory originally dealt with only bosons and did not include a description for the fermions. And 2. It predicted the existence of hypothetical faster-than-light particles, tachyons. These particles would travel back in time and destabilize space. Adding the principle of supersymmetry solved both the fermion and tachyon problem.
So,
what is string theory?
Okay. Right. So the string theory, exactly. What is this? This is a little joke with Einstein saying relativity is great, but I must admit that strings are more exciting. Well, Einstein actually never was already dead when the idea of string theory came up, but certainly he might have liked it because it's an elegant theory. The mathematics in it is very elegant, and it's something that people like because if it is confirmed true, that would show that the universe is an elegant thing and that nature is elegant. Now, since string theory is not complete, it's got some problems. Some theorists have come up with the idea of superstrings. And superstrings are strings enhanced with the hypothesis of supersymmetry. And what this means is that each particle that we have seen has a supersymmetric twin. So for each proton, there is an S proton. For a quark, there is an S quark, supersymmetric quark. Electron, there is a supersymmetric electron, and so on. And also the antiparticles, the antiprotons, for instance, the antiquarks, the positrons, the negative electron, the positive electron, they all have their supersymmetric twin. So let's let our friend talk about supersymmetry with their little animations.
Supersymmetry and superstring theory. The principle of supersymmetry says that nature is symmetric, and as a consequence, every boson has a fermion superpartner and every fermion has a boson superpartner. When supersymmetry is combined with string theory, superstring theory emerges. When physicists refer to string theory, they generally mean superstring theory, which describes all the fermions and bosons as being the result of vibrating superstrings of energy.
So supersymmetry, that is shortened to SUSY. So when you hear about physicists talk about SUSY, they don't refer to the daughter or the wife. They're talking about supersymmetry. Is the best candidate for detection in LHC. I mean, because it's impossible to detect strings. Strings themselves are way too small. They are so small that you can't even conceive. I mean, you need a detector the size of Jupiter to be able to detect something that small. You know that the smaller the thing you want to detect, the smaller the nut, the bigger the hammer, you need to crack it. And the same thing goes for particles. The smaller are these particles, the bigger the accelerator. So, however, if you hypothesize the existence of supersymmetric particles, those are particles that have about the same mass than the particles that we have. So they could be visualized, detected in the Large Hadron Collider. But so far we haven't seen any. However, we may do with higher energies. So let me lost my mouse. Here we go. So if we could find supersymmetric particles, then of course this would validate the whole superstring theory. Now, on the next, we're going to pass now on to the consequences of string theory, and there is the multiverse, the multiple dimensions. Just a word about these Calabi-Yau manifolds that our friend from the London City Girl will mention in the next animation. These are representations, mathematical representation of geometries in several dimensions. So you know that we are, this in fact, are only represented in 2D, or rather in fake 3D, because, or in 3D. You can do the same thing, of course, and view these things with a stereoscopic helmet and see them in 3D, in 3 dimensions. But you're still in 3 dimensions. You're thinking that in this kind of mathematics, in the Calabi-Yama mathematics, you can work in n dimensions. That means and according to the theorists, we actually may think that our universe has up to 11 dimensions. So imagine drawing something that is not based on 3 dimensions, but on 5, 6, 8 dimensions. So you have this kind of shapes that like turn over themselves because they don't have anywhere else to go in 3 dimensions.
Higher dimensions. We live in a 3-dimensional world, meaning there are 3 directions we can move in: forward and backward, up and down, and left and right. Einstein added a 4th dimension, time. When describing where we are at any given time, we combine our location in space with time. So, for example, if I wanted to meet my friend Janet for a coffee, there is no point in telling her I'll meet her outside Covent Garden Station if I don't also give her a specific time of when I will be there. Einstein combined the 3 dimensions of space and the 1 dimension of time and termed it space-time. In the theory of general relativity, space-time is described as the fabric of our cosmos. String theory proposes the existence of additional spatial dimensions plus the 3 familiar ones we experience in our everyday lives. In fact, string theory proposes 6 additional spatial dimensions that are curled up or compactified around every point in our 3-dimensional space. We can't experience them as these higher dimensions are so small we don't have access to them, but superstrings do. These superstrings oscillate in these dimensions in vibrating patterns that go on to create the matter and forces in the universe we see around us today. Higher dimensions. We live in
and again, here it starts. Sorry about that. Here we go. So she was talking about multiple dimensions. Now, there's a theory that that is called the brain theory, or M theory, from membrane. The idea is these dimensions, in fact, are nothing but membranes. Imagine sheets that ondulate like sheets in the wind. Imagine you hanging your laundry, your sheets in the wind. These sheets are infinite, and they can eventually touch each other. Now, these sheets contain basically everything that is visible. So we call them brains, for membranes, and brains is actually a shortening, and they are just part of a much bigger cosmos, reality, that is called the bulk or hyperspace. So strings, and therefore the particles that the strings compose or create, can exist only on one brain. We have 2 kinds of strings. In the picture I showed you before, there were like, you saw only closed strings, but there are closed and open strings. And these closed strings don't attach to the brains, and open strings instead attach to the brains and produce a different kind of interactions of the particles. So if you think of a brain like our universe, for instance, some particles are confined into our universe, into our brain. However, the graviton, which is a closed string, can actually go up through brain. So a graviton can, in theory, pass from our universe into another universe. Gravity would be then the only force that can go across universes. And remember when we spoke about dark matter, this huge concentration of gravity that we can detect in our universe, though we cannot see them. We can only see what it is. Well, those can, according to some people, some scientists, there could eventually be gravity that is sitting in another universe. That's why we cannot see it. But we feel the effect on our universe because the graviton can pass through. So when two parallel brains collide, they can trigger a big bang. And in the cyclic or ekpyrotic theory, this also I had questions before from you, and the fact that there may not have been a big bang, but a big bounce instead. And this means that basically the universe cyclically goes through big bangs and the big crunch. Basically it goes, inflates, and then eventually it comes back together and to start a new cycle of a new universe, a new big bang. So they start new universes every time they touch. So it's like a spark, that when this thing oscillates, they will eventually wave, they will touch and bang. They create a new big bang and a new universe. And that the universe bounces therefore at regular intervals, alternating periods of expansions and periods of contraction. The big inflation and then the crunch. And according to this cyclic theory of the M theory, I'm talking here about different groups, different opinions that scientists may have. I think that physicists are not always in agreement. Actually, they keep discussing different possibilities. So some propose certain ideas, certain theories, and others then others. So, and they keep discussing this until they have the proof. And that comes from experiments. And that's why CERN is there, to run the experiments that will prove somebody right or somebody wrong.
This is M theory or membrane theory, which is a theory that unites all the consistent versions of string theory. M theory brought all the string theories together by asserting that strings are really one-dimensional slices of a two-dimensional membrane vibrating in 11-dimensional space-time. This is a candidate for a theory of everything that many physicists support. And if true, it could represent the true nature of reality. Some estimates have shown that the number of multiverses predicted by this theory is 10 to the 500 power. That's 1 followed by 500 zeros. This is unimaginably huge. Now, this theory has some problems, though, like it predicts the existence of a subatomic particle called a graviton, which has not been detected so far. It also requires the universe to have up to 11 dimensions because the strings have to be able to vibrate in these number of dimensions in order for the theory to work mathematically. 11-dimensional mathematics is also so complex that the theory has been derided by many, including me, because its mathematics can be manipulated to represent almost any imaginable universe. But what if it's true? Maybe almost any imaginable universe actually exists. Maybe, given the number of physicists that support it and are working on it, could it be that they're in fact in the right track? Could they be onto something? But if this is really true, then where are the other dimensions? We only see 3 spatial dimensions and 1 time dimension. Where are the other 6 to 7 dimensions required by this theory? String theorists say that these dimensions may be compactified on a very small scale. So, for example, a rug looks 2-dimensional from very far away, but close up you can see that it has a 3rd dimension, a thickness, and it also has small loops and textures on its surface, similar to representing other potential dimensions. For example, if you go down to the scales that are closer to the scale of a Planck line, extra dimensions may be loops as shown on the grid here. Now imagine the loops being more complex shapes, like a Calabi-Yau manifold. This is a mathematical shape that can contain all of the 6 missing dimensions. Now imagine a string vibrating, not only in our 3 dimensions, but since strings can be really small, they can vibrate in these smaller dimensions as well. The way they vibrate determines the particles that they represent. One vibration can be a photon, another vibration can be gravity, Another can be an electron or other form of matter. In string theory, the strings and their vibrations are affected by the geometry in which those strings are moving. The issue is that the shape of those extra dimensions is not known. But if it was known, then the mathematics of string theory could tell you exactly what the vibrations would be. And this would give us a theoretical basis for why the parameters are the numbers that they are. In other words, the shape of the extra dimensions may determine the exact magnitude of those parameters. And if these shapes were any different, then the numbers would be different, and the universe as we know it would not exist. A different universe would exist, perhaps. Does this mean that the numbers could have been different if the shape of the dimensions was different? That is possible. Is there any way to test for these extra dimensions? It turns out there is, using the Large Hadron Collider. If after a collision of particles at extremely high energy, scientists detect less energy than was present in the two particles before the collision, then this would be an indication that the missing energy may have been transferred to these extra dimensions. So what has the LHC found? Well, so far the LHC has not found extra dimensions. But even if we found out the shape of the extra dimensions and determined that the math of string theory predicts the exact numbers that we measured, this may still leave the question of why the shape of those extra dimensions is the way that it is. So even if string theory answers the question of the true nature of the universe, it may still imply that there could be other universes where the shapes of those extra dimensions are different than what we observe. So why does our universe happen to be the way that it is? Why do we find ourselves in this relatively peaceful, orderly universe that supports life? Why should nature favor one kind of universe or one type of existence over another? There doesn't seem to be any reason for that. You could invoke God here and say that it was a supernatural force that caused this through his or her sheer will or divine intervention. An intriguing alternative and possibly testable theory is that we are part of a large multiverse, perhaps one of a multitude of membranes of the M theory. How could we test for this? The LHC could give us a clue. The soon-to-be-launched James Webb Telescope will allow us to peer farther in space and further back in time and perhaps find an anomaly that indicates the influence with another membrane. In the future, we may even be able to simulate multiple dimensions and universes. It may be that we just happen to find ourselves in that one universe out of innumerable other ones, where the shapes of our compacted dimensions happen to be such that life is possible. There's no other membrane where we would find ourselves. This universe perhaps is nothing special. It is but one of many possible universes that may number something like 10 to the 500 or more. And the only thing that may make this universe unique is that you are in it.
Yeah, we are in it. So, well, basically,
This is M.
it keeps going. Okay. How would you tell if we, how can we find things that we cannot see? In the detectors, this is an example of, for instance, of the CMS detector at CERN, which is one of the two detectors that found the Higgs boson. ATLAS was the other one, ATLAS and CMS. CMS stands for the compact muon solenoid. I will give you, I believe next time, I will give you a tour of CERN, of the Large Hadron Collider, showing you how it works, the engineering and the physics of the Large Hadron Collider. But because I realized that I've told you everything about physics, but I haven't told you much about CERN. So I'll do that next time. Now, how do you find things that are not visible? So one way is to understand the signature of some particles. So what happens is that the theorists hypothesize that if, for instance, a Higgs boson was to appear, the Higgs boson dies too fast. It just is created after the flash of energy, and then it decays immediately into something else. It just disappears. You cannot track it. You cannot see it in our detectors. But when it decays into other particles that, according to the maths, are predictable. And these predictions are called signatures. So for instance, the Higgs boson may decay in 2 muons and 2 electrons. So if you see 2 muons and 2 electrons, say, that was a Higgs. So that's how we found it, in fact. That's how we detected it, by looking at the signatures. And the Higgs boson has several signatures. This is the most common one, but there are others. So on the other end, there is something else that is kind of puzzling, is the fact that, you know, that by the principle of conservation of energy, which is the same in chemistry, you have to conserve whatever is mass and energy. I told you the analogy with ice and water. If you have 1 liter of water, it will give you roughly a kilo of ice, or a certain amount of ice. But when you melt this ice, you will find the same water that you had before. You know, that's, let's say, the principle of conservation, you know, and that applies to energy and mass. So if you have a certain amount of mass, like 2 protons colliding, you know that we'll have a certain amount of energy that is predictable, calculatable according to Einstein's formulas. E equals mc squared. You get the energy from the mass that you had in the beginning, and vice versa. You get the mass from the energy. So when you have less mass after a collision, and in particular when you see that your mass is all going in one direction instead of being symmetrically, you know, your particles coming out of the interaction, they go in strange ways. Then you may think that something has materialized, but you haven't seen it. So let's look, for instance, how we do this. This is a detector, the CMS detector. You see, it's huge. Look at the person down there, how small it is. That's a person down on the floor there. There are like 5 barrels like that. It's actually composed of 11 elements with 5 barrels. These are chambers of electronics that can detect particles. And you see they're arranged like an onion. You see here in this 3D model how these parts fit together, and then they close up. And each layer, a different color, can detect the different kind of particles. Of course, this is a crosscut. See, this is actually a 3D printed piece of plastic, a little modelino, model of the CMS detector, and you see the different layers there. Each layer detect electrons and hadrons, and you have hadron color readers there. The muons, these are the muon chambers. That ones are around here, the big ones, and so on. So each one is meant to detect a certain kind of particle. And there are though particles that are too elusive and they can't be detected, by this kind of detectors. So when you have a collision, this is a 3D representation of a real collision. This is the data that come out of a real. In fact, you see up there, it says the date when this event was recorded. You see that there is a collision in the center. This pipe that you see in the middle is the actual pipe that brings the protons together. So the LHC pipe that passes through the detector. And in the middle, these protons will collide and transform into energy and then create this huge sparkle, which is actually particles that go all over the place. And these tags down here, this blue long lines, etc., determine the energy that was recorded by the detector. So look at this event, which is a Higgs event. You can see these lines coming out here. The long lines are muons and electrons. That tells you it's in Higgs. And here you can tell that the particles are well balanced. So you find that they go all the different ways. You would say like on a perfect head-on collision, right? If you look at it from another angle, from a cross cut of the detector, from the center there, the cross cut right at the center of the collision point, you will see that this is so beautifully symmetric. Particles go in all directions. And look at this. This is an event of missing transverse energy, which means that the particles are all on one side, and there is a big hole on the left side where we hypothesize that something big escaped in that direction. but we don't know what it is. So this is kind of what can lead us to the discovery of something like supersymmetry or other kind of particles. To give you an example, let's take a billiard balls. Balls can collide, and then when they collide, they will go in opposite directions. Now imagine you have two balls that collide, and they both go in the same direction. Have you ever seen this on a billiard? Can this be possible? No, it can't, because of course the forces, I'm going to go back. This is a little animation I made in PowerPoint, so it's not so handy. Here, these two collide, and then the forces, will then carry them, obviously, with different angles. And this can never happen. That they collide and they both go down, unless there was another force like gravity, if the billiard was vertical, perhaps. But so when we find these events with missing transverse energy, well, they can be anything. It could be that we saw a neutrino, there was just neutrinos or dark matter, or it was like supersymmetric particle or something that we don't know yet about. So this is how exciting the research we're doing is. And it's on the fact that you are constantly looking for things, for animals. Imagine finding an animal that you've never seen before, a new species. Finding a new particle is as exciting as finding some kind of new species that you haven't completely imagined, on Earth. And with that, we get to the end of the presentation. And, tack för din uppskattning, Agneta. I'm thanking Agneta for her appreciation in Swedish. Okay, so Alex, have you been following comments? I've been browsing, but
I've only seen one question, really, which was early on. It said, "Is infrared light from the sun magnetic?"
Infrared light, is it magnetic? Well, it depends. Light is not necessarily magnetic. What you refer from magnetic is something magnetic is something that works with a magnetic field. So either you have a ferrite piece of magnetic metal, which is naturally magnetic, or which has been magnetized when being put next to a piece of magnetic ferrite, or you have a solenoid, which is an electronic, which a piece of wire that's wound about a nucleus of ferrite, and that is, of course, power. And this is generates a magnetic field when you turn it on. So, and that's what drives your motors, the electric motors, or anything that moves basically in electronically. So light by itself is not magnetic. Otherwise, if you had like metal dust, iron dust, it would be attracted to the bulbs. You see what I mean? And sunlight is the same thing. If it was magnetic, it would generate a magnetic field, which means it would take away from you your screwdrivers and other magnetic objects. So I would think no, it's not magnetic, although the photon is the carrier of the electromagnetic force, but that's because the photon moves as a wave. So, when you talk about radio waves, when you talk about gamma rays are a very high frequency form of electromagnetic wave. And when you call electromagnetic wave, it doesn't mean that the wave is magnetic, as in something that would attract objects, right? So that's what the photon does, is the carrier of the electromagnetic force, because it moves as an electromagnetic wave, which carries radio signals, X-rays, gamma rays, UV rays, whatever. I hope that I answered the question.
I'm not seeing many more questions at the moment. If you've got any question, guys, put them in the comments now, ideally in capital, so we can pick them out.
Okay, I'm seeing some opinions like Charlie Burke. Well, what can I say? Yes, well, it's your opinion. And I think you should probably visit CERN. CERN is open. You can go visit it and meet physicists that you can discuss with, talk about, and then make your idea if we're Nazis or not.
I've got one come up. Do the atoms in our body repel neutrinos as they pass through our bodies?
They don't repel them. The neutrinos pass through the atoms. When you look at an atom in the representation we give you, I mean, the ones that you see everywhere, you see this nucleus, and around it, just close to it, there are these electrons orbiting. But in reality, the scales are immense. It's like, imagine the nucleus was the Earth. If the Earth was a nucleus of an atom, then the electrons would probably be orbiting where Pluto is. So, there's a lot of empty space in an atom. And the neutrino just passes through, like not meeting anything. It does, of course, interact. Some neutrinos do interact. It doesn't know that all of them don't interact. Most neutrinos come from sources in the galaxy. They come from our sun. They come from supernovas explosion. In fact, there is one supernova in particular that is emitting them. And then they come from the Great Magellanic Cloud, for instance. There are some areas in our galaxy that are emitting a huge amount of neutrinos, and these neutrinos are everywhere. So they're being spread everywhere, like drops of rain during a really heavy rain, right? And they pass through the planet. They can pass through the whole Earth without interacting, without touching anything. Maybe the neutrinos that are passing now through me have passed through other worlds, through other, other planets before reaching me.
It's kind of follow on from that when someone said, "Where do the neutrinos go?"
I'm sorry, Dean?
Somebody said, "Where do the neutrinos go?"
Where do they go? Well, they travel throughout the universe forever. So basically, they go throughout the whole universe, and when they reach the edge of the universe, wherever that is, I don't know where they go then. Maybe they end up in a black hole. Maybe neutrinos can be absorbed, because neutrino does have a mass. So it will, even though it's infinitesimal, it's only like 2.2, I believe, electron. Is it kilo electron volt? It's probably, it was written in our slide before. Something like, it's something like 1,000 or million times less than a quark, or less than the electron, actually. Well, sorry, I'm not, what was the mass? There it is. It's, lost the slide. There we go. Well, actually, I can go here. Sorry, I'm going to go to the beginning where we had our slide. There it is. So the electron is 2.2 electron volt. Yes, I was right. The electron neutrino. Whereas the electron is 0.5 mega electron volt. So mega means million. So this thing is probably 500,000 times 2.2, 0.5. Another calculation. Well, it's several hundred times smaller than the electron. So this thing is going like it has a mass, although it's very small. So eventually they end up in black holes whenever they find, because black holes are so voracious. There's such huge concentration of gravity force that pull even light, imagine. And so, of course, they may pull, if they pull light, they can pull neutrinos. So maybe they all end up there. Think about something, for all of you who think that CERN is going to destroy the world. Well, give you an idea. You say with the black hole, some people accused us of making a black hole, and this black hole would destroy the world and the universe because it will eat everything. And we knew very well from the maths, from the theories, from everything, that these black holes would disintegrate, disappear in fraction of a second, because these are micro black holes that don't have sufficient mass to be able to become a real black hole. And that's what happened in 2000, in 2008, 9, we fired up the LHC, and we didn't get swallowed. The Earth is still here, and we've even made our LHC like twice as more powerful now, and we're still here still. So basically, the idea fell down the drain that we would swallow the universe. Now, if you look in the universe, there are about 1 million black holes moving around in our galaxy alone. They're just going like that, like vacuum cleaners, eating matter everywhere they are. And these black holes, of course, being celestial body moving in vacuum, they move at speeds of 20,000 to 100,000 kilometers an hour. Yes, an hour. So an hour in a second. No, an hour. So that means that one of them could fall near us, and then we end up in it within a matter of days, and there's nothing we can do about it. So, the universe is a very dangerous place where we live, We really didn't need nuclear weapons and climate change and AI and everything or whatever you may think of CERN to put us at risk, because there are so many risks coming, asteroids or like I said, black holes from the universe.
Okay.
But there's nothing we can do. We just need to be philosophical about it. Touch wood. That no black hole eats me tonight.
You've gone on, I think it's still on neutrinos, but do they travel in a pattern?
I wouldn't think so. They're completely unrelated. Neutrinos, they generate the shot out of any kind of matter to energy, disintegration of matter to energy. That's why they come from the sun. The sun is the biggest. Well, the sun, our sun, or any stars are actually nothing but nuclear power plants that work on fusion. As we saw, gluons, that are there. Gluons are keeping together the protons and keeping together, protons and neutrons in the nucleus. But gluons, once you force them, squash them by the enormous gravity, what happens is that they fuse and they become pure energy. And so when that happens, there is a massive emission of neutrinos everywhere. And these neutrinos, like I said, will be shot and travel through planets or through stars or through anything, through gases in the universe. And eventually some of them reach us, but they don't think that you can say they travel in patterns.
Okay. What's the story with anti-gravity research right now? 75 years and nothing, ?
Anti-gravity, you're talking about antimatter, maybe. Antimatter is being researched. Anti-gravity is in the science fiction films. Because in order to produce anti-gravity, which is supposed to be what spaceships, UFOs use, right? To keep up there without making a noise or anything. So, that's, if you look at every science fiction film involving aliens, that's what they do. But anti-gravity as such is not a field of research today. That's simply because if we don't understand what gravity is, how do you want us to make anti-gravity? Eventually, one day, when we will find the graviton, then we will probably know if an anti-graviton exists and if this is the carrier of anti-gravity. What we're working on is antimatter. This we produce at CERN. We have an antimatter factory. Look at my episode on antimatter. This antimatter factory synthesizes anti-hydrogen, which is anti-hydrogen but with the opposite sign. So hydrogen is one proton, positive, and one electron, negative, plus a neutron. Anti-hydrogen is the opposite sign. So the proton is negative and the electron is positive. Now, this antimatter is unstable in our universe because it will annihilate when it gets to touch matter. So if you were to get antimatter and somehow pour it in a bottle, it will immediately disintegrate against the atoms that make the walls of that bottle. So when we make it by using we decelerate antiprotons that are formed by collisions in a particle accelerator. So we decelerate these protons and we take them, really go slower and slower until we can trap them in a magnetic field in a bottle that's about a bottle is huge big thing of, about 3 meters by, 80 centimeter inside. I mean, there are several of these traps and different sizes, but when they get in there, they will go and the magnetic field will make them oscillate until they finally block them. They freeze them. And then we bomb them with the positrons, which are positive electrons. And eventually, because they're oscillating, they will start turning around. And so we synthesize an atom of anti-hydrogen, hydrogen the opposite way. And why are we doing this? Because it's the only way to study them. These things don't exist in our universe. If you want to study them, to understand what happened at the time of the Big Bang, you have to make them. So goes for all the other particles, the Higgs, etc. If you want to study them, you have to make them. And you can only make them by colliding protons together on this planet.
Okay. Not really seeing any more questions. I've got just one. I'll admit that some of this goes over my head, and I'm not saying it doesn't, but I've spent way too many hours watching the whole Big Bang Theory. So is there anything actually in super asymmetry?
Is there anything, sorry, what? Is there anything?
You talked about supersymmetry today. Well, there's a big thing on the actual Big Bang Theory.
You mean
program.
have we found anything?
Is there anything actually in their theory of super asymmetry they come up with?
Supersymmetry is a theory still. That means, like all theories, it needs to be confirmed by experimentation. Like I said in the last slides, what we're looking at, trying to find out when we have an event of missing energy. That means that we have an event and we have some particles, and then where did the rest go? Imagine you got 2 billiard balls, and then these things you have to find 2 other billiard balls. Well, billiard balls, they don't disintegrate when they collect, but particles do. But the conservation of energy or conservation of mass, which is the same thing, tells us that if you collide so much mass, which is a proton, with so much mass, from everything else that crystallizes out of the flash of energy, there must be in total the same amount of mass or energy of the 2 particles that collided. Nothing can be created or nothing disappears. But when the scales don't measure, they find that the particles we get are less than the sum of the 2 protons, then we've created something that we don't know what it is, and that escaped, and we cannot detect. Our detectors did not find it. So again, these things that the LHC created are so small and, on the scale, so small and invisible that immediately they disintegrate into something else and eventually become an electron or a neutrino, a proton, a quark or something. So yeah, supersymmetry has not been found, but we hope that this kind of analysis of this transversal energy one day could bring us to identifying a supersymmetric particle, which would validate the whole string theory.
Okay. One more just pops up, so we'll make that the last one probably. Do you think we'll ever find the graviton particle?
Well, yeah, that's a good question. The graviton, like I said, only a few years ago there was some experiments, not at CERN, LIGO, etc., that managed to find to discover. It's been not too long, last year or something. Sorry, my memory, I'm too old to remember when. But lately they found they could measure for the first time gravitational waves. Think this was due to two colliding galaxies. So imagine, galaxies can collide. Again, between the atrocious things that happen and the total, holocaust that happen everywhere in our universe, it's not only black holes, but 2 galaxies can collide. When they collide, in this case, actually, they were rotating. They were, before getting to collision, they started orbiting around each other. So these two galaxies started doing this movement. And this created such a huge ripple in space-time that started doing like the waves in the water when you throw a stone. You throw a stone in a lake, you will see these waves, concentric waves that go. So these guys were rotating in a way, they were creating these waves. And we measured these ripples in space-time, ondulation of space-time, that got all the way to us. And so now we know that gravity can actually be seen as a wave. And as we know from quantum physics in general, whatever is a wave also has a shape of a particle. Particles can be waves, and they have this double identity. They have two faces. One day the wave in a certain condition, that wave in a certain condition, they look like particles, and it all depends on what the observer does. So yeah, you may think that if gravity is like the other forces, then you may think that, yes, there is such thing as a gravity, but we have never seen it. So far, we cannot say that it exists. Science only can tell you that things exist after they've seen them. When I say seen them, it's not seen with our eyes. Detected is a better word. They've seen them in our detectors, the computers that look at the data in the detector could actually detect them.
Okay.
Yeah, I can see some question. Was Albert Einstein a Mason? I have no idea, honestly.
I didn't know if that would be within your thing of span of knowledge. That's why I hadn't picked that one up.
Okay.
Other than that, I think I've covered most of the ones that they've asked.
So yes, that's another thing I wanted to say before closing this episode, is that again, I have a lot of friend requests on Facebook, but most of them are fake, the hustlers. So please, if you want to send me a friend request, the man from CERN on Facebook, send me a message saying that you are a Jacobite. And then I'll accept you, because I'm not accepting people. There's hundreds of requests from people that are suspicious. Pretty girls in bikini and other guys that don't know what they want to sell me. So, and the next time won't be next week because I'm on holiday. It will be the week after, I believe on a Monday. I go back on Monday. Today was exceptional. And we will, like I promised, I'll take you to a tour of CERN to see the Large Hadron Collider in particular, but also other experiments like the antimatter factory, etc. I will describe some of the exciting things that my ex-colleagues are doing. They're having the fun. I mean, I'm having a different kind of fun now. I live in the Indian Ocean, so I'm going kite surfing and boating and diving. Okay, I guess it's a different kind of fun. But I missed that one a bit. So thank you very much, everybody. And I'll see you next time on this channel. Thank you, Alex, for mediating.
Good night, guys.